Okay, I think it's already time to start our lecture. So I welcome everybody on this lecture course. And our fifth lecture will be given by Professor Eric Herbst from University of Virginia, and he will speak about the chemical process in space, histories, and current understanding. So please, Eric, the floor is yours.
Well, thank you very much. So let me start. Whoop. Okay. So I start with the same introduction, the same title, Chemical Processes in Space, Histories and Current Understanding. Now, you're supposed to be looking at the so-called Hubble Deep Field. It's a picture of pretty much a big section of the universe. And the reason I put this slide up is just to indicate that molecules, which is what we're going to be talking about, are found in many areas in which we look for them, in particular our own galaxy, but external galaxies as well. So we will really discuss then what molecules tell us, where they are found, and then see what might happen in the future. All right, so this is a very simple picture that you probably have seen many times, but I include it anyway. We're talking now about a region of what we call interstellar space, in which we have clouds of gas and dust, and we have stars forming, and we have lots of molecules. So let me just go over this picture here. It starts from a stellar system such as our own, and out of this comes a star, which is born and then dies, and then we go around again sometimes. So let's take a look when the stellar system gets rather old and becomes, loses the planets and especially the star in its midst, loses material. And the so-called mass loss comes out and eventually, over the eons of time, forms what are called diffuse clouds, which are partially transparent and have cooled and do show us some molecules as well as gas and dust. But eventually, then what happens is these clouds start to collapse, and that's the picture here you see is the so-called dark cloud. That's we're looking at a condensed cloud that has a temperature of 10 Kelvin or something like that, and molecules can be seen. What is next seen here is what I've shown as a giant cloud. This dark cloud is one single cloud. The giant clouds is very, very large and is divided up into lots of regions, and lots of small clouds and stars are being formed. And so we won't really worry about that one versus the single cloud. But eventually what happens to all of these clouds, whether they're little ones or big ones, actually collapse to form stars. And this is first, the collapse goes through what are called protostars, in which the clouds heat up and we have so-called hot cores. And then eventually from this disk comes a star is born, and the material around it, because of gravity, becomes planetary, and we call it a disk. And eventually we have, again, the stellar system. All right, so that's a very simple way of looking at it. Okay, so let's move on. Now, this is a real picture of dark clouds towards the center of the Milky Way, our galaxy. And you can see all this dark stuff because it's again a contrast with these very bright stars here. And the bright stars, in the visible anyway, cannot go through the black stuff. But the black stuff can be seen if it has if the stars behind it have infrared and radio waves. So, by the way, this is also, I believe, the so-called Magellanic Clouds. All right. So instead of looking at this whole big region, here is one region of space. I called it a dark cloud. It's a part of a dark cloud. Anyway, a complicated region called TMC1. But you see here this dark stuff that looks like it could be nothing, but it really isn't nothing. It is gas and tiny dust particles, and they block visible light, but they don't block longer wavelengths. There's the infrared and the radio, and the infrared and the radio tell us a lot. Mostly, until recently, I would say the radio tells us the most, but infrared is becoming very important as well. And here's some information. The dark region here has a very low temperature, 10 Kelvin above absolute zero, and the density of 10 to the fourth per cubic centimeter. That is a very, very low density. I used to say to people that it was a perfect vacuum, low, that anything could be done on Earth. But it turns out that's wrong now. I was told by a speaker that you could actually get to an even lower density. But just remember that the density in the room where you're sitting is billions and billions of, well, the density is very, very high. So 10 to the fourth is a very, very low density. And it's very rare that molecules and atoms come and hit each other and perhaps react. So the most abundant molecules, just to name a few, in molecular hydrogen and carbon monoxide, but this in the gas. But there are many exotic molecules, as we'll see, both in the gas and some in the on surfaces of dust particles. All right, so how do we see molecules? For those of you who weren't trained in spectroscopy, this is a picture of a diatomic molecule. A diatomic molecule. These are the nuclei. They're small, but I draw them big, and they undergo certain motions. So this motion is to represent vibration. So the nuclei, along with everything else, they're vibrating. And then what else is happening? Well, there's also rotation. So end over end rotation, which I indicate here. And then these little dots here are supposed to be electrons, and they move around. Now, each of these motions, electronic, vibrational, rotational, gives off electromagnetic radiation. And the electromagnetic radiation is the radio, that's the radio, and then the infrared, and then the visible. So the radio has the lowest frequency. The infrared is in between, and the electronic in the UV visible. Okay, is certainly the most powerful radiation, but the shortest wavelength. Just like the radio is the longest wavelength and the infrared is in the middle. Now, molecules can either absorb these particular frequencies or they can emit frequencies. So astronomers looking for molecule signs can look in emission compared with everything else, or they can actually see this radiation being absorbed. So that's two ways of doing it. We call them absorption or emission, and they can each tell us about what the molecules are. All right, well, the first detection that we know of molecules by spectroscopic techniques are these so-called diffuse interstellar bands. Diffuse means that these lines here are spread out a bit. They're wide. It's not like a diffuse cloud. And anyway, so they're broad. They're seen in absorption in this spectrum, and there are now about 500 or more of these so-called lines, and which we can see on the Earth. And anyway, one molecule has been assigned to some of these lines, and that's a very strange molecule. It's like fullerene, which is 60 carbon atoms, but one of them is a missing electron, so it's C60 plus. And it is certainly assigned because we can also see it in the laboratory. But then we can jump a long way from the year from that year into the year 1950. In 1950, or around that time, slightly before 1937 to 1941 to be exact. And these are three very unusual molecules, and they are in diffuse clouds. And in the diffuse clouds, light could go through and we can see in absorption. Okay, so these molecules are seen at special frequencies, the CH, CN, and CH plus. Very strange. You can't find them in stable form on the Earth. And here is the telescope that was used. All right. But moving on now we get more and more molecules by the years 1970 and 1980. And so as the slide says, it's the start of molecular radio astronomy. So most molecules have been seen in space using what astronomers call radio. It's not really, the wavelengths are more like millimeter waves or even submillimeter waves. So they're a little smaller in wavelength than radio, but that's what they're called. And the telescopes that see them are called radio telescopes. So starting in 1968, by Charles Townes, ammonia was seen towards the center of the galaxy. And here are some very important landmarks. Water was seen in a variety of these clouds, and this is a big one, Sagittarius B2 and Orion, but they're also seen in smaller regions. Here's formaldehyde. Here's carbon monoxide seen. And here is the first ion, HCO plus. And this, astronomers didn't know what to make of this, so they called it exogen, and that means it's sort of unknown. And well, it eventually was learned that it was missing one electron. And the last one I show here is methanol. Methanol is a very interesting molecule. It is seen both in the gas and on the surfaces of dust particles. And finally, and most importantly, in a sense, the most abundant molecule is molecular hydrogen. That was first seen in the ultraviolet. Okay. Now, the story of exogen is an interesting story, so I thought it's an amusing story also. As I said, 1970, this molecule, whatever it was one frequency seen by Snyder and Buell at 89 gigahertz. So this is radio astronomy. And my research advisor said that he knew that the molecule that was doing the emitting, and it's HCO, hydrogen, a carbon, and oxygen with a plus sign. And the reason no one believed him. I certainly didn't. I was a loudmouth student. And what one can actually tell from radio astronomy or from the spectroscopy on the ground is what the structure is like. And the structure appeared to be nothing like what you should be seeing. So everyone said he was wrong, that he being the research director, but he published it anyway because he was a well-known person. And then what happened was another spectroscopist by the name of Claude Woods, who was still active, actually measured this in the laboratory, which means that he measured the same frequency as was seen in space. And so he proved that HCO plus is in one of these clouds. Now, how my research director got it right with everything else he said about it was wrong, I don't know. I just said, so maybe a genius is someone who gets the right answer when everything else is wrong. But in any case, that was the first ion that was seen, and there are now many ions that are seen. All right, here's a picture. This is Klepera, the person who got the assignment right. This is the Nobel laureate, and the Nobel laureate is Gerhard Herzberg. And I don't know if you could see me now because suddenly the lights have gone off. Okay, well, let's hope you could be seeing me. I'm not sure. In any case, these are, if you can believe this, the person on the right is myself. Doesn't look at all like me now. So just an amusing slide here. All right, so here is a here is a picture. Really, it is a spectrum taken by a very, very old now, very small single dish. Single dish means one radio telescope on the ground, and it's seeing lots of spectra. This is like a radio. These are what we call emission lines. All of these emission lines have now been assigned, okay, to different molecules. I don't think there's any problem in this region of the spectrum. Now, from the point of view of chemistry, chemists realize that some of the molecules are very unusual. Some are just like molecules on Earth. And what you're seeing is the intensity of these various spectral features. But there are some very exotic molecules, which are molecules that astronomers wouldn't think are exotic, but chemists would, such as CCS, or C4H, and then there are even more exotic species. So this is a very interesting slide because it shows very interesting new molecules that have to be detected on Earth to make an assignment believable. And also we learn from this how much of each molecule is around. We learn how the area is moving because the frequencies and the Doppler effect are different from those on Earth. So one learns an awful lot from spectra that are taken of molecules. And this is the radio spectra. So you're seeing a rotational motion. Okay. Now, nowadays, instead of a single dish, we could use many dishes in tandem. And this is the father or mother or whatever of all of these large, what are called interferometers, because the radio waves from the ground into the telescopes have to be combined to get more intensity. And this is in a mountaintop in Chile. And they can be moved. And the reason why you want to move an interferometer, move these individual telescopes, it depends on whether you want to see very high resolution objects that aren't so far away, or you could see very, very distant ones, depending on how close together or how far away the telescopes are. So this is clearly an improvement over the old single dishes. All right, that was in the radio. So infrared got started also, and this is an infrared space, it's a European satellite, infrared space observatory. The problem with doing infrared radiation studies from the ground is our atmosphere does not like infrared radiation. There's too much water vapor, even in a desert. And so what we have to do is we have to have, for the most part, satellites surrounding the Earth or even farther. And then it can be beamed to the Earth and analyzed. So anyway, here's a collection of molecules. The spectra are rather broad compared with what we saw from the radio ones. And this is now mostly in the infrared. And the infrared, you can actually see dust particles, the molecules in dust particles. And dust particles themselves. Anyway, infrared radiation to see spectra just requires a moving a dipole. In other words, the molecule has to vibrate and have a vibrating dipole. That's not difficult. In a sense, it's the radio has to have a permanent dipole to be seen. And so in the radio, we cannot see molecules that don't have a dipole. In the infrared, we can, as long as the dipole is going back and forth. So it's very different in that sense. So they complement each other, as well as in frequency, but as structure of molecules, whether there's a dipole moving or just a permanent dipole. Okay. So onward. So this is now the latest in infrared telescopes. It's JWST, it's called, and this is a picture of it. And it is, again, this is not on the Earth, obviously. It's not really surrounding the Earth either. It's farther away from the Earth than that. Anyway, it has been going now for 2 to 3 years and has started to pick up a lot of new things to complement what can be seen by this ALMA, this interferometer that I showed you. All right, well, here's a picture. This is not really a picture of space. It's just some of the molecules one sees and just spread out. And here, which we're going to go over shortly, there are two main types of molecules that are seen. These are all organic molecules. That is, they have carbon and they have lots of, well, they have up to 6 atoms or more, which astronomers tend to call complex, but which isn't complex to organic chemists. But anyway, one set of molecules you could see is linear, okay? And the chemist shows that there are weak bonds and then there are strong bonds. In addition to the linear ones, which are called carbon chains, we have these other type of molecules here, which have structures that are nonlinear, and some of these are called aromatic hydrocarbons. Okay, we'll get to that too. So this is just a picture of some of the molecules that can be seen. And this business here is just a really part of this torus structure. All right. Why, this one is moving, it seems. Okay. All right. So most people now, when they give talks about interstellar molecules, put that line up or put on into a table over 250 of these molecules, and I don't think you get any information that way. You can't look through and see everything before the next slide comes. So anyway, here's how I do it. I just pick groups of molecules that are similar, and then only a few of the more important ones. So I start off with molecules in the gas, because there are many more in the gas than on the surfaces of dust particles. So first I start with simple molecules, and these simple ones, as you see here, okay, they start off with molecular hydrogen, and ammonia is here. And then we actually have what are called cations by chemists. They're missing a charge, and this is H3 plus. And then there's a deuterated version. One of the hydrogens has switched to deuterium. Here are our carbon chains. These really look crazy when you can actually see the structures. Lots of carbon atoms, up now to 10 carbon atoms in a line. And then we have the complex organic molecules that aren't complex, but they are organic because they have some carbon. And some of these molecules were actually seen in the previous picture because they're not linear and they have different structures. Chemists and astronomers, astrochemists, are very interested in these molecules because it's thought that may indeed be precursors to life. All right. There are even bigger molecules, the so-called fullerenes, and these polycyclic aromatic hydrocarbons, which consist of multiple benzene rings. Benzene rings are hexagons. In the ice, the number of molecules, it's harder to be seen, only seen in the infrared. Let's go back again. Okay, and so the biggest one is methanol. Unlike in the gas phase, which they get considerably bigger, but still it tells us an awful lot about what's going on dust particles. So these dust particles have a bulk in which you can see silicates and amorphous carbon. Then there's a surface which goes down about 4 layers or so. And that is mostly water ice in the cold regions of space. Now, some new results from this JWST. A lot of this is astronomy more than astrochemistry, but one sees these disks, which eventually will become stars. There are exoplanets. You can see these things, and you can see the molecules in the gas around them. These molecules these are simple ones that are well known. This one is very unusual, but we're talking about molecules that don't have dipoles. So they have vibrating dipoles and can be seen in the infrared. And recently I saw some statement by a scientific writer that huge organic molecules were found in a young external galaxy by this JWST. I don't know what they mean by that. The biggest molecules that one could see all over are these polycyclic aromatic hydrocarbons or fullerenes, but I'm not sure if that is the answer or whether the spectroscopy was done correctly. Okay. So now we have, this is another view of a star. This starts with a diffuse cloud and ends up with a new star. And one goes through all the stages here, similar to that first slide I showed you. We have a diffuse cloud, and then there's a dark cloud, and there's collapse of various types. And then we get eventually a star starting to form, and surrounding it a disk which is flattened by gravity, and eventually one comes up with so-called a protoplanetary disk in a solar system. Now, the important thing from the molecule standpoint is these complex organic molecules, which I told you chemists, astrochemists think may indeed be precursors to life. They were only found for a while in the hot regions, something called the hot core, up to 300 Kelvin or so. Okay, and why does this? Okay, whoop. All right, so. Okay, so at first they were all seen in hot regions. Then these comms started being seen in all the regions, and I've used letters. So CC stands for carbon chain, C stands for comms, etc. And the point is that now pretty much molecules are all over. It's just a question of what the abundances are in one source compared with another. So, for example, these carbon chains, which we only thought were in these diffuse clouds, are now seen in all sorts of regions, and the comms are seen almost everywhere. And so it's a much more complicated life, much more complicated system than we thought before. So all the way from the diffuse clouds to the formation of stars and planets, we do see complex organic molecules. All right, now this is towards the end of the story here, in which the story of what's happening, and it's showing the end. This is a part of the story. It starts from coldish regions, and eventually we have class 0, class 1, class 2, class 3, and these really are delineated by the fact that the disk is forming. As the disk forms, that's in the orange, and there's material going off perpendicular, shown in blue, and eventually one gets to the planetary system. Okay. So anyway, it's often in astronomy, it seems to me, but not trained as an astronomer, one always starts with class 1, and then there has to be a class 0 when they see someone that's young, some star that's younger than pre-stars that's younger than class 1. Okay, so anyone very interested in comms can look at this in the latest Protostars and Protoplanets volume. All right, so now something a bit on the history of basic reactions. Now, there are lots of chemical reactions going on. They both form new molecules and destroy them. And so some of this is just the type of reactions. There's formation on dust particles, and the most abundant one is molecular hydrogen. And then in the gas phase, one has reactions between ions and neutral molecules. One can indeed also have chemistry on the surface of grains, and one can have what are called neutral reactions, two neutral species, not an ion and a neutral species, seen, okay, these are seen in the gas phase. And one always has to remember in chemistry that a lot of reactions take place with a barrier. So here's a barrier, and that slows reactions down. whether it's in the gas phase or in the solid phase. And so there's chemistry, there's clearly quantum mechanics in which we see tunneling under barriers. So all of this has to be taken into account if one is trying to understand what molecules are around and what they can tell us. Here is a picture that's probably too much to read, but this is a chemical reaction in the gas phase, and the rate of a chemical reaction, say it's the rate of forming species Y, there's a derivative here, concentrations of the reactants, and chemists don't like cross sections. So physicists like cross sections to get rates of reactions. Chemists like so-called rate constants or rate coefficients. And many of these systems have barriers, Boltzmann-type barriers, which slow them down. And ions, when they react with neutrals, typically are not slowed down. And so we have a lot of different types of things happening between ions and neutrals in the gas phase. Okay, so that's another interesting thing. And if I had more time, I could talk about experiments also as to what goes on, so that you know what machines can actually look at very low temperatures, cold gas in the interstellar space, but this is, of course, in laboratory, and that can go down to temperatures that near 10 Kelvin. Then there are somewhat older systems like the SIF system, which is thermal, and crossed beams in which two beams come together to collide and react. And then a so-called merge beam in which the two species reacting come together at a very low angle. And so that's called a crossed beam. But it's merged, and you can actually get a lot of information from the fact that they're merged. All right, and then if one wanted to look at these rates of reactions, they have a K, which tells us the so-called rate coefficient or the cross section. And this is too much information, I think, to discuss here, but it tells the chemists working on trying to make models what the rates are as a function of temperature, and whether they're in the gas or they're in the solid. And if in the gas, do they have ions or only neutrals? So it's a very complicated picture. All right, so what we now do when we have so-called chemical simulations, we look at any type of region in the interstellar medium, such as we can look at clouds collapsing, we look at what happens afterwards. So, and we get a lot of information just from either calculating or measuring the rates of reactions. Reactions forms gas, and they form surfaces, and they destroy gas. And anyway, as a function of all the rates put into these simulations, one indeed can get spectra and abundances and compare these with measurements. And the two state-of-the-art, very big systems. One is called Magical and one is called Nautilus. These are interesting names, but both Magical and Nautilus were done by postdocs of mine who were in the group at the same time. So both Magical and Nautilus came at the same time. And these are then had thousands and thousands of chemical reactions. I should say that the first model of this sort, in which we calculate concentrations with a big computer, nowadays, when I first did it with my research advisor, we got up to 100 reactions. So now we have about 100 times 100 reactions. And we can compare with observations. We can learn about physical conditions of sources and their history. All right, moving on. So here's an example of some chemical reactions. Here is one involving cosmic rays, high energy protons that smash into H2 and make H2 plus electrons. And this H2 is very reactive and leads to a chain of ion molecule reactions. And eventually leads to water and OH plus longer pathways, which there's no time really to discuss. So here's an example of what happens with H2 plus, eventually gives you H3 plus, and eventually you get these bigger molecules, the ions, and they react with electrons and they neutralize, and these also are very important in making not only these COMs, but in also making these carbon chains. So these are very important to put in these chemical simulations. All right, well, here's a complicated example of, whoops. Okay, this is what I would call, this is called a neutral system. There are no ions in it. This is in the gas phase, and it's a complicated series of reactions that leads to a bigger molecule called methylformate, which is here. Okay, and we did a preliminary study, and this was the beta study in the chemistry that leads from methanol, which isn't very big, to this molecule. So it has all types of reactions in the gas phase and on surfaces. So what about surfaces? Well, here's the formation of molecular hydrogen. The two hydrogen atoms can come and stick at low temperatures, move around, make molecular hydrogen, and then molecular hydrogen eventually comes off. And this actually has been studied in the laboratory, but was first thought of as an idea by the late Salpeter, well-known physicist. And then it's much more than just two hydrogen atoms. Okay, one can have say, CO coming down and reacting with an O to make CO2, or H and OH to make water. So these things build up, and eventually over 100 monolayers of various molecules are formed. Now, here's a very cute picture showing what happens when molecules or atoms come down to grains. They move around in very random patterns. And then eventually some of them collide and stick, and then perhaps they heat up and go back into the gas phase. So we have dust particles. Some people call them catalysts. So they can start from gas phase stuff, and by accretion have reactions on surfaces. And then if there's some warmth around the surfaces, can be well, the accretion is they're no longer around. The molecules diffuse, come together, and then come off into the gas. But here's a more detailed one that I drew a while back, showing this. This is a one-dimensional picture of what really happens. So what happens is two molecules have to accrete, and they have to find one another. And they do that by going over barriers. Now, there are two types of barriers on surfaces. The surface itself has barriers because they're bonded. The surface stuff that is more strongly bonded in some places. That's the potential minima, and then there are potential maxima. And then in addition, the molecules have their own activation energy. That is the potential barrier I've shown you before. So it's a rather complicated picture for surface scientists to figure out what happens. And the diffusion, the simple diffusion, is called the Langmuir-Hinshelwood mechanism. And then there is another mechanism, the Ely-Rideal mechanism, in which we start with a molecule here on the surface and something else comes down from the gas, and they can have a reaction that way. All right, and then we have plenty of reactions that can occur on the surfaces. Typically, the ones that move, the atoms or molecules that move the fastest are indeed atoms like oxygen, or radicals, that is not stable neutrals like OH. These reactions have been studied by people. So we begin to understand what was actually happening on the surface of dust particles. So we now have chemistry in the gas, we have chemistry in the bulk of grains, and we have chemistry on the surface of grains. So it's getting more and more complicated. All right, now, so here's what people think. There are two ways to form these complex molecules, COMs. And this is just showing star and planet that's eventually being formed from a diffuse cloud. And this is the temperature, it's cold, and eventually then it heats up and stuff can come off. It's a complicated picture whether or not the chemistry occurs on the dust or the chemistry occurs in the gas. And depending on the scientists you talk to, they will argue one way or the other. So probably both form molecules, but the big molecules are seen in the gas, which means even if they're formed on dust, they have to somehow get off the dust and get into the gas to be seen by the radio. All right. So for many years, well, not many, I shouldn't say many, about 10 years after these molecules were first seen in the hot regions and people thought they understood why the temperature, why things goes into the molecules go into the gas, because the temperature goes up. Well, unfortunately, as I said, carbons and all other molecules can be found anywhere. And indeed, they now seem to love 10 Kelvin. So we have very cold molecules and warm molecules. The cold ones were seen about 10 years, I suspect, a little more than the warm ones. And they're seen in regions in between. So the chemistry is getting more and more complicated as to how you can do this. So we're not going to have time to really discuss this for the most part, just to look at the fact that the chemistry is very unusual. Okay, so I and others have found very unusual types of molecules. And for example, radiative association in a very diffuse gas, diffuse by terrestrial standards, two molecules could actually come together and stick by giving off a photon. This is very popular, by the way, in nuclear physics, but it's very rare, and maybe only occurs in space in this type of gas. Anyway, so there are others. There's electrons sticking to neutrals. There are neutral-neutral reactions with very unusual rates. And we'll take a brief look at that. Okay, so this is picture radiative association. The idea is two species come together, and before, if they're big, they last a long time, and they have time enough to actually emit radiation and stabilize themselves. Here are several people that have actually tried to measure this type of process, but it's very difficult. So it's mostly done by quantum mechanics anyway. So we think that these radiative association reactions are very important at low temperatures, not at high temperatures. And so they may have something to do with why molecules can be seen in low temperature regions. Here's this is actually a quantum mechanical calculation done by a student of mine. This is the reaction CH3 plus CH3OH, and the rate constant, which remember is related to cross section, is shown on the ordinate, and the abscissa in temperature. And you can see these reactions do like low temperature, because at low temperature, what chemists call these intermediate reactions, these intermediate processes, stay around along that they can give off the radiation. Okay. All right, here's another very unusual molecule. This I'm sorry, not unusual molecule, unusual reactions. So typically, if you have neutral reactions, then as it goes to lower temperature, this is a plot, the so-called rate gets slower and slower and slower, and by very low temperatures, you don't have much of a reaction at all. And here are examples that are getting slower and slower, and then appear to have changed their minds, and then they go faster and faster again, and soon they go on every collision at low temperature. So these reactions become very important because low temperature, there's a lot of low temperature chemistry. So it's very interesting. Chemists have worked on trying to understand what's going on. So we don't really have too much time to discuss it, but it's a process in which the two reactants come together, and then there's a barrier. But before there's a barrier in the potential, there's a well, and then the system tunnels under the barrier and comes out, okay, and forms products. So it's very complicated when you have a well and a barrier, and that's what we think is why they have such strange temperature dependence. But these are then important in forming low temperature species. So there are a lot of these unusual low temperature species which we think occur and then can help make these combs at low temperatures as well as the better understood high temperatures. Here are some types of surface reactions, okay? There are reactions that have diffusion on the surface, but they don't really move. So they're called non-diffusive. They don't stick together. Some of them, some move, but some don't. And then there are metastable species. That means in the gas phase, they're in non-singlet states, and they come and react actually on a surface. Radiolysis, oops. Radiolysis means is another process in which molecules are bombarded by cosmic rays, and they form ions, and the ions are on the surface now because radiolysis the cosmic rays have no trouble going through dust particles. So ions are formed by collisions of cosmic rays with neutral species. The ions react, and one can make these combs by radiolysis. There's photodesorption, that is, molecules actually hit the surface and kick off something. Sputtering is a more fierce way of getting rid of molecules off and into the gas. And then there are unusual surface reactions that can actually form larger molecules even than glycine. So it's one way of forming, one of many ways. I don't have enough time really to talk about some of these. This is a system of partial diffusion. The oxygen and the hydrogen can react quickly on a surface, they're light, but they form an OH with not reactive, except that the OH and CO are very close to one another. One is right on the surface, one is right below it, and so they don't have to move at all to react. So that's what's called non-diffusive reaction, and that's what actually probably makes CO2. It was first done by a French chemist, Toulet. Here is a picture of radiolysis. Okay, so cosmic ray protons smashing into this is actually theory. It's a very complicated theory to try to show this, as you could guess. But as the cosmic rays go through and make ions and neutrals, break them up, then one gets secondary reactions. And this people have calculated and also measured. So there's a lot of radiolysis. It's very popular to measure these things because they do lead to carbon and atoms. And as long as you have some cosmic ray protons and some other things that have carbon atoms. So anyway, so that's yet another way of making these comms. And then there is desorption with photons. I mean, the list is very, very long, and one could write a book about it, or at least a long research article, which I already have, but it keeps getting more complicated. Here is something that was measured a few years ago at 10 to 15 Kelvin. You start off with radicals, which are quite reactive. So O is important, H is important, CO can be important, N important. Anyway, it's a sequence of reactions which are mostly non-diffusive. That is, they're so close to other molecules on a surface that they don't have to diffuse to find each other. And so, I mean, this was measured, and the top is glycine, and it's gone past then. Unfortunately, the person who led this effort died a month or so ago. It's very sad. Okay. All right. So there are so-called position. These are very complicated Monte Carlo calculations. You follow individual species randomly, and that takes much more time than simple kinetic collisions. But that is also done by people. that for various reasons. Okay, some of you may have heard of machine learning. Okay, I have two students that prefer to use machines, the so-called machines. That is essentially, this is done by theory, and the theory gives what percentage of species are likely to react and what are not, and you do this by actually just do this. It's in a sense, it's a random process with machine learning techniques that I know very little about, but the students do it. And there was a contest we had about two years ago about trying to make a model by the standard method, our kinetic method, building up to form C10H minus. So one of these carbon chains with a negative sign. And that was done by my students, and they used the machine learning business. Okay. And the machine learning, it was about a tie. They first said that machine learning was faster than humans, but it wasn't really. They had made a bit of a mistake. So far, we can't guess who won, but my students are going to look now at the much larger instead of very simple systems, they're going to look at very large cores with lots of chemistry, and we'll see what they can do with machines. All right, one final slide here, which some of you may have seen this. I like this idea. It's called the uncertain future, because the future really is uncertain. So this was done by an American politician. But anyway, here it goes. As we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know, we don't know. So life can be more and more complicated. Okay. And I end with acknowledgments of collaborators and students, and they're divided up into standard astrochemistry and to machine learning. So that's it. Thank you very much. We have about 10 minutes, I think, for questions. Thank you.
Okay, thank you, Eric, for very interesting and informative lecture. So please ask all your questions in the chat. And meanwhile, while you are writing your questions, I can already start with my question. In your presentation, you said that quite often in space we can find very unusual molecules, which you cannot simply go and buy in shop and easily measure its spectra in order later on to detect it in space. Would it be possible to do the quantum chemical computation of spectral properties of these molecules and use this computation for the detection of these molecules in space?
Yes, it's uncommon, and the reason is, I don't know, you probably know more than I do. It's getting closer, but it has to be very, very close to the prediction. These predictions, what we're thinking of, we're not sure. It's how close can you actually get with a structure? Do you get 1%, or I haven't followed. The answer is it is possible, and there have been possibilities to this sort of thing. That I believe H2D plus was an example. But yes is the answer, but it hasn't been done very often. Typically, it's easy. It's done by people doing spectra in the laboratory, and then
Yes.
that because it's closer.
Okay. So you would, in principle, believe in such identification if it's just based on the computation?
It really depends, right? It depends how close how close they are together. It depends on there are some clouds that there's such a high density of lines. It's very tricky. You could calculate something and within the uncertainty find a number of lines. It's not just one.
Okay. Thank you. So now let's go on to the questions in our chart. So on slide 20, the reference is the same as the first slides. Is it the same reference on the slide 20 and on the first slide? Yeah, that was the question.
I'm sorry, I don't understand. Is that for me? That
On slide 20, the reference on slide 20 is the same as on the first slide.
okay. Let's see. All right, we will move it to slide 20. Okay, so this is now partially theory, partially various experiments. It's just showing what happens to actually form these disks, and eventually the disks become stars, and the stars and planets. So the first slide is just showing what's it's hard to say, we can see external galaxies. It doesn't have to be just in our galaxy. So there is some information. There are astrochemists that do study close in, but external galaxies. If that's what you're referring to. Can you see these various stages? What you can see is molecules which are we think belong in certain regions and not in others. So the temperature could be different, the densities can be different. So in a sense, right?
Okay, thank you. So the next question, considering that the most of the ISM reaction are gas phase type, how do catalytic reaction in the ISM affect, and usually what material are known as a catalyst in the ISM except for the materials in the dust and grains?
Right. Well, let's look at it this way. In the gas, okay, if you want to take a density of 10 to the fourth per cubic centimeter and ask what is the time in between collisions, you have, very, very long times in between collisions. So it's not obvious to see, I don't know if one should even use the word catalyst. It's I think these are rare chemical reactions, but the clouds are very big, so you still get you still build up molecules. I don't know if it's really the word catalyst is that meaningful in that sense. On the surface, it's perhaps more meaningful to say that water. You have a lot of water ice. And that does seem to promote molecule formation. So maybe you would say that was a catalyst. It's not what we're used to in chemistry but it's close, I think. But in the gas phase, it's very rarefied, and you would have if you wanted something as a catalyst, it would have to stay around for a long time, and it is doable, I think. But it's 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 an interesting question. Perhaps the questioner knows more about catalysts than I do. So
Okay, thank you. The next question. I wanted to ask if there was an upper limit to the length of carbon chains that can be formed.
well, in the laboratory, the Thaddeus laboratory, I think got over 20, but I'm not 100% sure of that. But bigger than the C10 in space. So that's 10 carbon atoms in a line and negatively charged to boot is very unusual. Right? So I don't know if there's, I think people who have measured these things, as they get bigger and bigger, then the carbon chains actually couple up and form non-chains, right? All you need is the two ends coming together, and then it's closer to a calm than it is to a chain.
Okay. Thank you. So the next question. I wonder about the radiative association process. Is there any research group observed the emitted radiation? If no, what is the major difficulty?
The major difficulty is it has to be very low density, because otherwise you get three-body association. What happens at not low density, you get two. Let's consider you have two molecules. They come together, okay, and they don't come together very frequently, and so that's hard. And then if you have a third body coming down, you form a three body. If the third body comes down, say as it would in the laboratory, it's very hard to see radiative association as opposed to three-body association. Now, I didn't have the time, but I have a slide showing this business as a function of density by another scientist who's died, unfortunately, Dieter Gerlich. And you could see that I think it's believable. Some people don't believe it, but anyway. If anyone is interested, I can send this. I think I have that slide reproduced in one of these review articles. And essentially, it has a region. If you plot the rate against temperature, against density, excuse me, in high density, everything is saturated. So you have 100% reaction. In mid density, you have three-body reaction. And at low density, you seem to have a two-body radiative reaction. So, but I don't know if there are several people. There is a person at the University of Maryland who's trying to measure radiative association. But it does exist because in nuclear, you see, and then you have to have a reasonable Einstein A coefficient. That you need too. So that's why nuclear physics wins in this, because you have gamma rays coming off, so it's faster.
Okay, thank you. So the next question, I'm not completely sure, so I will read. I presume no one has found, and here it's written Na, I guess it's sodium. Is it because it is not there or because we need a better technique?
There's lots of it. In fact, we had we found sodium chloride. So there was an article on table salt. There's a lot of sodium chloride, but there is sodium, yes.
Okay. Sorry.
Well,
I just found an explanation of this question later on. It was not about sodium. It was DNA.
oh, okay, fine. Yeah, well, I don't know about DNA. That's above me.
Okay. Okay, so the next question. Most molecules that have been shown are formed by carbon, hydrogen, oxygen, and maybe nitrogen. Are there not molecules from other atoms?
Yes, there are. But uh, if you look at you look at a star, and as I showed, as stars old, they get older, they blow out the stuff. But there's each element has a certain abundance, certain concentration, and the most abundant ones are the ones that were named. I mean, hydrogen is very abundant, and so is helium, but it's not very reactive. And carbon, oxygen, and nitrogen, and then the next three most abundant ones. So you're dealing with abundances. People have found lots of lots of sulfur molecules, though. So you could see sulfur molecules. You can see bigger ones. It's just harder. They're not as common. it's just like on Earth, right? I mean, most molecules are organic molecules, right? Even though the processes of making these things are quite different. So,
Okay, thank you. So the next question is again about the slide 20.
okay.
So I will read in slide 20. What is the main cause of creating very strong gravity in interstellar clouds for the formation of star? What factor causes disk-like stability around the star? Is only a reasonable space distance from the poles necessary, or are other things needed?
Well, first of all, right, it's clearly it's rotating, right? So you have a bias towards going towards a flat surface. This is flat. I mean, it doesn't. This picture doesn't really show it, but it flattens and then it as okay, so it flattens, and so gravity is very important in space. It's hard to believe, but it is because if you have lots of species around, it's slow, but it's earnest, shall we say? So you do have to calculate these things to see, what can happen over millions of years. Right?
Okay, thank you. So again, the question about the slide 20 from another person.
It's not even my slide. Go ahead.
Okay, but this question is about this reference, and what does PP 723 means, because people try to Google
Okay, there's
this
a yeah,
reference.
right. Yes, it's very easy to get. I think PPP stands for protostars and protoplanets, so something like that. And it's been a series of books on topics. And this latest one, I believe it's just recently published or will be published. There was a conference in Japan about this. So this one is also it's a lot about molecules. And for example, if you wanted to know, are there molecules here that are different from molecules here? Well, of course, the temperatures are different, so that will be. But molecules have been measured in all, let's say, almost all of these species, and they're not the same. And the densities and the temperatures are very, very important in making these comms. Because remember, with the comms, nowadays they're in the cold regions too, as well as the warm regions. And these are in between. So this is sort of these in between regions that also some have more molecules than others, but they do have these molecules.
Okay, thank you. So the next question about machine learning. Who won in the prediction of abundance of C10H minus, machine learning or standard kinetic approach?
Well, the
And
machine
what are, okay.
No, I'm sorry, continue. I interrupted. And
what are other possible uses of machine learning in astrochemistry? Yes.
Well, I think one of the group who did the machine learning could probably answer that question better than I can. So if you write a question, I'll give it to her. But she's now looking at a one of these very giant clouds, which has lots of different physical conditions, and so you don't expect the same sort of thing as in the simple uni-cloud pictures, which they use this TMC1, which is a very simple, relatively speaking, region, a low density region. And so it was relatively easy. And that's where carbon chains are found. In these bigger molecules, they're much more complicated. But I think she submitted a paper on this. But it wasn't a contest this time. It was just what she was doing. So
Okay, thank you. Yeah, I just want to remind that yes, we indeed have Slack channel where you could ask more questions and then probably get more answers. So the next question, are the surface reaction on dust grains necessary to the formation of large molecules,
Oh,
lysine or
you're
other
talking.
amino acid?
Okay, if you want to read a chat, this PP7, and it's come out, I think I have it in, if it's not illegal, I have it on paper and can send it to some. But some people think surface chemistry is more important. Others think gas phase chemistry is more important. They both have very good reasoning, and you can find both of them in this volume. Or if you want, I've written, but I think it's better to get this volume. It's been a series of volumes. So 7 means, I think, every 5 years or something like that. So this is the 7th version. It's very useful to astronomers. So
Okay, thank you. So the next question, in one slide, you showed a spectra with 500 lines. How could one assign all these lines without ambiguity? For instance, for infrared spectra, it is mostly based on the functional group rather than specific molecules.
yeah,
The
yeah.
CH vibration frequency may have similar frequencies. How could this be distinguished? Yes.
Okay. Well, I can, let's take methanol. Before I did astronomy, I did radio spectroscopy. I would call it millimeter wave spectroscopy. And although you have thousands of lines, you do a very good job these days of agreeing with measurement and an assignment. So that I think radio has really improved, but I think you're right about the infrared. I mean, I saw a slide the other day of a young student, and she measured methanol with this new dust telescope, this JWST, and she assigned 5 lines. So in the same region of space, we could assign, say, many times that for methanol. And it's because the theory is very well understood, but it's not going to be 100%. No, no way. I mean, if you take a look nowadays at some of these radio spectra, I mean, they're very dense. So yes, I sympathize. Getting 100% is impossible, but identifying a molecule is fairly easy.
Okay, thank you. So the next question, is there an upper limit to molecule size that cannot be exceeded in space?
Good question. Good question. I don't know the answer to that. I mean, it's well, there was that one slide I showed from the Leiden group. It was, and at the top of that picture was glycine, but really, the picture keeps going. I mean, so that group was still increasing in size. We have seen C60, right? And that's pretty big. So I don't know the answer how big it could possibly be. So we are at the C60. I think C60 is the limit so far.
Okay, thank you. So the next question, are three-body collisions between atoms, molecules, and three-body recombination important to consider in modeling the early universe or any other astrophysical conditions?
Well, the 3-body stuff, I think, would have to be reasonably high density compared to the radiative association. So anything having to do with a star or close to a star is high density, right? But there you also, if it's too hot, that's not going to help. So you still want it to be somewhat, you want it to be cold and you want it to be high density. You don't want it to be pressure. And you don't want to have a barrier to these things. But yes, people do see three-body systems. I mean, it's not uncommon. I mean, it's sometimes some people think of it as a pest, that you can't avoid it. But certainly, if you're trying to see radiative association, you have to be very careful that you're not seeing the three-body association. But there are apparatuses that let you distinguish at very low density. Mm. So I didn't have time to go over all the different apparatuses that people use.
Okay, thank you. So the next question. What are the major shortcomings of the traditional rate coefficient chemical models compared with other models like MCMC and machine learning?
Right. Well, you have a group that knows that knows the answer to these questions, and I'm not one of them. So the big group next right adjacent to where we are, this University of Virginia, is called the NRAO, National Radio Astronomy Observatory, and they do this sort of thing. So, okay, if you you can look them up. And they understand this sort of thing much better than I do. So
Okay, thank you.
it's yeah. So that's why if you want to, give me a question and a detailed question, and I can give it to them. I can certainly give it to my student. I mean, so she, in fact. You can look at, she's actually published one paper, and that's on the C10H minus business. And this other one is coming out on this very dense giant molecular cloud. And that has lots of predictions, so I don't know how accurate the predictions will be. So we don't do that. We do other things that are unusual, like Monte Carlo methods, and but it's becoming a very wide field. So certainly
Okay.
there's room for many more people.
Okay, thank you. The next question is rather basic. So about PAHs, can you explain the meaning of aromatic and polycyclic?
Sorry, what was the last word? I didn't understand.
Can you explain the meaning of aromatic and polycyclic?
I don't know what the last type of molecule is.
No, it's polycyclic aromatic hydrocarbon. So
Yes.
people just want to know what does it really mean,
Oh,
polycyclic and aromatic in the term of polycyclic aromatic hydrocarbons.
I see. Okay, I'm not an expert in that either. People do that for a living, and and then they worry about all sorts of differences. And so there's a big group at NASA Ames in the U.S. that does it. There's let's see, in France, there are places that do it very in very great detail. I mean, I can look up the names, but the older I get, the harder it is to remember names. So but yeah, in Toulouse, there's a group in France that does it. So people work hard at it, and but still, it's again, it's tough, difficult.
Okay, thanks. So the next question, you mentioned the upper limit of the size of the molecules is C60. Would this limit be applicable to PAHs as well?
They're different, right? They are different. The C60, is simple in the following sense. I mean, despite the fact that it has 60 atoms, it only has 4 infrared transitions, if I remember right. that can be detected, right? Whereas C60, you get all sorts of transitions, right? I mean, I'm sorry, for PAHs, you get many. It's a much harder spectrum to get. So I'm not sure. It's that and here's what happens. Okay, for PAHs, the vibration also you can look at molecules and see that they're likely to be PAHs from their infrared spectrum. But seeing what infrared spectrum, that's harder. C60 is easier because you don't have much of a choice.
Okay, thank you. So I have also a short question. So the detection of the molecules in space in the infrared range, would it be better be based on the emission or absorption of the molecules? So
Well, it's the same as with the radio. It really depends on the background. So if you have a strong background in the infrared, you could see absorption, right? If you don't, but you have energy, you could see emission. So, or you could see both because of the way, uh, I've been talking without light, by the way. So I hope I got things right. But in any case, now the light has come back on. So that's the answer. Normally it's very complex. So suppose you have a star right in the middle of something, and you have molecules surrounding it that are in the there you have molecules say that go out east and west, and we are in the south. So in other words, there are systems in which you can see both, right? So depending on where the bodies lie.
okay.
So it is hard. It is hard to. You really have to work hard to understand all of this. By the way, there are masers in space, and that's a very hard one too. In fact, some people suggest that most molecules are weak masers. There's a group in France that does believe that. In Paris, Saclay. Yeah.
Okay. So then we can really see very intense radiation.
Yeah.
Okay, thank you very much for answering all questions. Oh, okay. Okay, so I don't see basically currently any further question in the chat. And yeah, then I think we should thanks our lecturer
Okay.
very much for very clear and interesting talk presentation. Thank you, Eric.
Well,
And
thank you for having me. I like this very much. These longer talks, you can really get highly involved. So thank you. Anyone wants to do a written question, that's fine. That happened last year too, when we did similar things. So, because then I can actually look up better references if I'm not the one who did them, and so that's fine if you want to ask a question, and yeah.
okay, then thank you, and then see everybody on the next Thursday for the next lecture number 6. Yeah. Thank you.
Okay. Thank you.
And